Yeah, welcome everyone. We're just going to give a few more minutes here to allow some more time for some more people to come in, but we will get started right away.
Let me know when I should kick off.
Yeah, we'll get started in a second here. Okay, let's get started. Welcome everybody. Thank you so much for joining us today. We have a really exciting hour ahead of us with another Filecoin masterclass. And this happens to be one of the most requested ones we've had so far. So it's going to be a really great hour with a lot of great information. So let's hop right into it. I would like to start by introducing Michael, Rod, and Chris from Protocol Labs. And they're going to be the ones taking us through how to prepare large data sets for Filecoin storage. So with that, Rod, would you like to get us started?
Yeah, sure. Okay, so I'm Rod Vag, and I'm with Chris, and Michael's also here as well. We are on the IPLD team. Now, IPLD is the middle layer of the stack. It's concerned with the data layer and how we connect pieces of data together in a distributed fashion. My talk today is called Content Address Data Structures with IPLD. This is a really basic primer on IPLD. I hope that a lot of this material is already familiar to folks listening in. If not, then this is a great chance to get up to speed. One of my aims with this is to try and get folks a little bit out of the standard IPFS frame of thinking and into thinking more about how to think about content address data structures and how we link pieces together to form these complex graphs, and not just jam everything into the IPFS way of building graphs. So when Chris has his talk after mine, he's going to talk about how we use these approaches to process extremely large data sets and do it in a very parallel way so that they were suitable for storing in Filecoin Discover. So with that, I'm going to start and I'm going to rewind right back to the beginnings of content addressability and some of the basic terminology and things that you may or may not be familiar with, just to set the scene. So let's start off and talk about Merkle trees. I'm assuming that most people listening in have the very basics of content addressing, that a content address is really, in our world anyway, it's a way of addressing content by looking at its hash, hash digest. So content and hash have a one-to-one relationship, and we can look up content by having the hash. Now, the term Merkle trees comes from a patent that Ralph Merkle filed in 1979, and the basic idea of a Merkle tree is that you could have a hash digest embedded within hash digest, and you can form this tree-like structure. And what this means is that at any point in this tree, the address or the hash of that point authenticates all of the linked data underneath the tree. So you can have a single hash that references many hashes underneath it. Now, importantly, the original patent diagram has this classic style Merkle tree where you concatenate hashes to form this very pretty binary graph. A Merkle tree is not just a concatenation of hashes, although commonly in the real world, like in Bitcoin and other places, you'll see the term Merkle tree used for a concatenation of hashes to form this very, very clean binary tree. A Merkle tree really just means a tree of data where there are hashes inside nodes that authenticate other nodes, and they bring them in through this linking mechanism. So you can get these very sloppy structures and still call them Merkle trees. A DAG is something you might have encountered in Filecoin documentation, but we use this term a lot. It's directed acyclic graph. It comes from graph theory, not necessarily to do with content addressability, but it's a useful concept. So what it really means is you have a graph of nodes. It's directed, so there's directionality to all of the links. So in graph theory, you can have bidirectional graphs as well. A DAG is directed, so the links only go one way. And it's acyclic. There's no possibility of cycles within the graph. So you can't link from a later node back to an earlier node. It fits really nicely with Merkle trees because of hash functions. The hash function gives us directionality. They're a one-way operation. You can only go from, in theory anyway, from the hash of the data to the data. There's a directionality. And there's no cycles. You can't link to data that doesn't already exist, that you don't already have a hash for. You can't leave a placeholder for a hash. It gets baked in, so there's no cycle. So we often end up with terms like Merkle DAG or DAG by itself or Merkle tree. So these terms get thrown around a bit, but this is what they mean. Now, to bring it into something a little bit more concrete, this is a classic thing that people often want to do with content addressed data structures, build a file system. And this is very similar to the IPFS way of building a file system, and many other systems will do similar things. So in this example, we might have 8 files. Each file would be addressed by the hash of the data. So we just run a hash function over the data. That gives us an address. So we have 8 different things that we can address. And then we pull them up into 2 different directories. And we include the hashes of the files that we want in those directories inside the directory metadata. So we might just have an array of hashes, and that might be our directory. Maybe that's all we're hashing. And we hash these directories as well, whatever form they take. And then the hashes of those directories become addresses that we can then point to. So our file system in this very simplistic example has 10 independent chunks, each of which has its own address. And there you see a directionality there, and you see lack of cycles as well. So this is a DAG. This might be familiar if you know anything about Git. So Git, this tree looks very similar, a little bit more complicated. But in the lower levels of the Git format, we find exactly the same thing, where you have what are called trees, and these are essentially directories. And the trees point to blobs, which are essentially files. And you can have trees pointing to other trees, but all the way at the bottom, you have these blobs. The blobs get hashed, and Git uses SHA-1 at the moment. And the SHA-1s get included in these blobs, which point to other blobs, which point to trees and blobs. And you hash them, and you include the hash of these trees within the actual commit. And then you hash the commit to get the commit hash that we're used to seeing in Git. The commit itself contains not only a link to the tree and its blobs, and therefore it's blobs in a Merkle fashion, but it also includes other metadata like the author, committer, and the message. And it also includes a link to the previous commit. So in this way, we build this tree that grows over time and can mutate over time. So in this example here, I've got on the left-hand side, I've got the newer commit pointing back to older commits, and you can see that I'm mutating my files over time. So in the first commit on the right, I've got 4 files. Second commit, I've added 2 more. Third commit, I've made a subdirectory and put them in subdirectory, and I've deleted a file and added some new ones. But I'm still pointing back to some original blobs, and I've got some new ones, and I've got this directory structure. So this is a very, very familiar pattern in content addressing that you'll see repeated again and again. These acyclic graphs and using Merkleization to authenticate the data all the way at the leaf by including it at the top. So IPLD comes in here with some primitives that we think help with building these structures. And the first one is CID, which is our extension of a hash digest. And the CID is content identifier, and we use this to be a self-describing content identifier, because a hash is really just a hash digest is really just an array of bytes. It could be, there's a number of different lengths of standard hash digest and different hash functions as well. So and we also don't know what they point to without the context of that. So a CID gives us a lot more information in this array of bytes. So we prefix the CID with a version number first, so we can version CIDs and potentially add new features in the future. We add a multi-codec that tells us the content type. I'll talk about that in a minute. And that tells us essentially what the hash is pointing to. What is the hash of? When we get there, what will we find? And the CID also includes a multi-hash code. So this is tells us what hash function was used. And that multi-hash also includes the length of the hash, so we can see that right up front. We know what the length should be and how many bytes to expect in it. There's some links on the page there that will and they're in the Zoom chat as well, that will take you to some of the specifications for these things, and also there's code repos for these things as well. To break that down a little bit further into something that might be more familiar, CIDs can be represented as strings, and we use this thing called multibase, and that's just different ways of representing different base strings. So because we've got an array of bytes, we need to turn it into something we can actually print. So we use multibase to do that. The CID I've given you there at the top is this is in base 32, and you'll often see this is the AFY prefix. It's a very common prefix that you'll see, which will be clear in a minute. But the very first character tells us something important. It tells us in this string, it tells us what base we have. So in this, we've got the B, and in the multi-base table, we can look up B and say that's base 32. We can use that then to decode this string into the bytes, giving you the hexadecimal there. In those bytes, we have the original hash, the original content address, and I put that in bold, and that's on the right. This little prefix tells us a lot about what's going on. So if I work through the prefix, I've got, first of all, the version, CID version 1. It's the first byte there, which is just 1. The second part is the codec, which is hexadecimal 70. And that tells us that the data we're pointing to is DAG-PB format, which is the typical IPFS UnixFS file format. So we know what this thing's pointing, what type of data this thing's pointing to. So when we get there, we can decode it. We can pull up the DAG-PB codec and say, decode this binary. The next little bit is the multi-hash. So it tells us the hash function, SHA-256, that's hexadecimal 12, and then the number of bytes that it consumes, and that's hexadecimal 20, which is 32 in decimal. So then we decode those 32 bytes. That gives us the hash that we can use. Then when we load that binary, we could rerun the hash function and verify that it's the data we expect. So this is what a CID is. And they're very flexible. We do all sorts of things with CIDs, and you'll see them a lot when you deal with Filecoin, in some novel ways too. Now, CID has a version 0, which is you'll commonly see around the web. This has been deprecated, and we wouldn't advise you actually using these in anything new. But when you encounter them, you'll see them. They start with Q, the capital Q. That tells us that multibase is base 58 ETC, and we can use that to decode the rest. CID version 0 assumes DAG-PB. It doesn't vary on the codec, and it also it forces you SHA-256. So when you load a CID version 1, you know it's DAG-PB, and it will be SHA-256. So this is the typical UnixFS for IPFS format. Everything newer is using the CID version 1, and you would be recommended to use that very strongly because it contains a lot more information. The second thing that IPLD brings is codecs. Now, we use a table to map integer codes to codecs. A codec tells us how to decode and encode binary block data. And we have a lot of different codecs, and some of them, a lot of them are not ours. We've got our own codecs, but codecs can be generic, like JSON is a codec, tells us how to decode strings into object data. CBOR is another one designed specifically for binary, and it's much more compact. And also just raw bytes. If we have like video or something where we don't actually want to decode it into a data form, we want to do something else with it, we use raw bytes. And this is used a lot in Filecoin Discover that Chris will be covering as well. A lot of raw bytes in there. Codecs can be other content address formats that include their own implicit linking types like Git and Bitcoin block. we can view them through an IPLD lens and interpret them with our own. We can put CIDs when we instantiate data out of them. So we have some code that will interpret these things and give us CIDs when we read them. But these are not formats where we can write CIDs into them. But they've got their own hashes in them, and it's just we know what those hashes point to. And then lastly, we have IPLD native codecs. DAG-PB, DAG-CBOR, and DAG-JSON are the main IPLD native codecs. DAG-PB is used for UnixFS in IPFS. You'll encounter that a lot. And most of the data we did for Filecoin discovered DAG-PB and RAW. DAG-CBOR is if you're building something new with that's not using just plain file data. This is a good recommended codec. It's compact and very flexible. If you do all sorts of data shapes, it'll basically allow you to put almost any data shape into block form. DAG-JSON is not something you'd be recommended to do with data you have a lot of, because it's not very efficient, but it's an interesting format to look at least. So moving on, let's get back to our example of the file system we're building. I want to point out this concept of a graph root, because this becomes a really critical concept when you're talking about managing large amounts of data. So in our example, directory 1 would be our graph root. And this means that this is the single thing that we need to hold on to address the whole lot. Like in the Merkle tree in the beginning, we only need directory 1 in order to be able to address and authenticate all of the files in our whole tree. So we don't need to have references to all of these things in an index somewhere. Directory 1 serves as our index, and we can traverse through the graph to get to everything we need. We could also use directory 2 as our index if we only cared about that subgraph. Perhaps we only cared about these 4 files. We could just grab directory 2 and use that as our root for whatever purpose we need our root for. A root is fairly arbitrary when it comes to these graphs, because graphs can be very large. They can span across multiple graphs. We might only want subgraphs. Or we could make an entirely new directory and reference only part of our other graph that might still exist. So maybe we make a new root, add 2 more files to it, and point to a subgraph of our original one. So a root is this thing that we hold on to, and it's something that contains everything we care about for a particular purpose. So in this example, we care about 4 files down the bottom and 2 new files. We've got this one root that points to them. Roots are important if we care about mutability. And I know it's funny to talk about mutability with content addressing, but mutability is something we can build into these essentially append-only data structures by caring about the root. So if we change the root, we can make things mutable. So in this example, I want to say edit file number 1. Now I can't edit the bytes because the hash will change. So what I end up doing is making a new blob and hashing that, and then I have to include that hash in its parent, which is directory 1, and then that gets a new hash as well. So essentially, I'm making 2 new nodes, but I'm still referencing 8 different files. One of them is different to the original, but I'm still referencing 8 files, and I've only created 2 new nodes. So I've got this mutable file system going on here. And a neat feature of this kind of behavior is that we can actually use it for snapshots. We could use it to roll back in time. If we built in some notion of garbage collection, we could get rid of the old nodes we don't care about, and we could change this over time. IPFS does some of this stuff natively, but it's important to think about roots and how a root references the tip of your graph and the most important thing you care about. Mutability extends to everything you want to change with a graph. So in this graph, it's some kind of arbitrary B tree. Maybe it contains file data, maybe it contains something else. Maybe it's nicely formed. It's got rules about how it's formed. If I want to add, delete, modify, do any operation with this thing, I just need to care about the root and how these modifications bubble up through the tree to give me a new root. So if I've done a bunch of edits in this tree and it's given me a new root, I've done some deletions, some additions. I'm still referencing the bulk of the old tree, but I also have some new elements. And again, I've got this snapshotting. I can look back in time. I can change which root I care about for which purpose. Maybe I garbage collect old things. But you can see what I'm getting at here, which is this concept that these Merkle trees bubble up to the tip, and it's the hashes that also bubble up as well. I'm going to quickly walk through an example. This may or may not be helpful, but what I want to get at is thinking about how we build algorithms and data structures that can span very large sizes. In this example, it's fairly simplistic, but it does actually extend to a real data structure that we have got specified. So I want to build a super large array. I want to build an array that can live in content address land, and it could be arbitrarily large, but we want to interact with it by pieces. So perhaps this thing is so large, I couldn't fit it in memory. Perhaps it's so large, I couldn't even fit it on my own disk. It has to live out there in Filecoin, perhaps, or perhaps in some other content address space. So this thing is fairly generic. I'm not caring about how it's encoded. That is a separate concern. I'm building an algorithm here. And the things I'm storing in this array are also generic. They could be links to other objects, or they could be simple values, or they could be something else. You know, these things, they come into the picture when you've got a concrete use case. But in this example, I'm building an algorithm that's generic. So let's start off with the naive case, which is let's just put everything in one block. Now that obviously falls apart when you get to large sizes because your blocks become unreasonably big. And in IPFS, if you're storing in IPFS, then the recommended maximum is about 1 meg. I think there's a actual maximum of 2 meg because of bit swap, but your advised maximum is about 1 meg. Now, the size of your block will depend on your use case. Perhaps you want smaller blocks for other reasons because they're faster to load, but there's various trade-offs with block size. But I can't just pack all of my elements into one block, so I need to have a way to extend beyond the block. So what I'm going to do is I'm going to say there's a maximum width of my array in a single block. Any block in this array can only get up to a certain width, and I'm going to fix that in my example to 5. So if I start off with 4 and then add another one, then I've got my maximum sized array here. This is full, and in both the first and the second, I've only got one block, so therefore it is my root. My root is my graph. If I want to, and when I want to mutate, it gives me a new root, which is a new version of it. So if I maintain within 5, then I've still got the 1. If I want to push beyond 5, then I have to start building a tree. So in this algorithm, I'm going to add a second sister block, also up to a maximum of 5. And then I'm going to address both of those blocks in a parent block. And I'm going to call this a height in my graph. So I've got a height of 2. And in my height of 2, I can fit in 5 blocks of data, each with 5 elements. So that gives me a maximum of 25. So for any height, I can work out, and for any width, I can work out the maximum I can fit in with the equation width to the power of height. And in this example, width to the power of height, that's 5 to the power of 2, which gives me 25. So here is a graph at full capacity at height 2. I've got 5 different blocks, and I'm addressing them all in my root block, which has the addresses, and I'm saying they're hashes here, but there would actually be CRDs in IPLD. My elements in my height 2 are just links to my height 1. My height 1 contains the actual elements I care about. If I overflow that capacity, I have to add a new height. So in this second part, I'm adding a new element. I've got 26 elements now. I've overflowed. Now I have to add a new height, height 3, and my new capacity is 125 because now it's 5 to the power of 3. So you can see with this scheme, I can keep on going out arbitrarily large. It just means I also have to get higher at the same time. And all it does is take me to a new single root. I've got one node I can hang on to, and that gives me the address of everything in the entire array. Now that's well and good, except that I want to be able to generally get to the individual elements of these things without loading them all. So I have to have some way of getting from the root to the element I care about. So this is where we build algorithms to do this. So to traverse from to a particular index, I need to jump from the root. I need to say I want element number 19. I have to know where to go to in my first jump and then where to go into in the second jump. And I've got an algorithm for that here. The details are not that important. If you want to read up on this, I've got a link at the end to a specification for this particular algorithm. Essentially, I take each node as a separate thing, and when I perform a get operation on that node, I need to work out which bits of that index I need to chop off that I care about and which bits to pass on to a child node. And so in this example, I've got to figure out first which child node do I navigate to get to the index you care about. And then when I figure out which child node I'm pointing down into, I need to know what the new index is to give to that child node, because it's not going to know when I get to the base level and I've got, say, the 5th element along, and I'm saying I want element 19, it's going to say, what? I don't even know where I am in this list. I'm just a free floating block with 5 elements. I've got to be able to tell it, I want the 4th element along in your array. So at each level, I've got to change my little index there. So there's an algorithm for doing that will get you closer and closer as you get towards the end. And it leaves you with these blocks that all they are is arrays, hashing arrays to provide links, and they're using CIDs for that. And there's no other metadata included in any of these blocks. They're just arrays, which is really a really nice format because it gives us some nice properties. It also gives us some unfortunate properties, but these are trade-offs we have to care about. So let's look at some properties of this algorithm. Larger width means larger blocks, but also fewer levels. So your traversals could be quicker, but your load times of blocks is larger. So you've got some trade-offs already in considering how wide your blocks need to be. And there's also a mutation cost there. If you're adding one element at a time, you're also discarding blocks at the edge of your array at a rate of up to the width. So there's garbage collection costs there as well. Get and size operations are efficient. That they use that roughly the algorithm I already showed, which allow you to traverse just one step each down to height 1. And for size, we want to traverse all the way out to the edge to see how big each at the trailing edge they are. Appending data requires mutating a maximum of only one existing node up to one existing node per level. So when we append data at the end, we get this hash thing bubbling up to parent levels, and that's a nice property. It means we're not modifying huge chunks of the data structure. Iteration is really easy. It just becomes a left-to-right tree traversal, and you just put this in the shape of a tree, and you just do the left-to-right recursive, really nice traversal. Slicing is only efficient if you perform it at the boundaries of the width. So if I want to take, let's say I want to take the 10 elements from the middle of this array and make a new array, that would be really easy if it fell within the width boundary. So if I want to take element 6 to 15, then I just need those two blocks, and I need a new parent block to address them. That's all I need. If I need anything else, then I'm going to have to start shuffling things, which is essentially rewriting the whole lot. So it gets a bit messy. Pre-pending data is equally costly because you end up rewriting stuff. There are ways to do it efficiently if you were working at the width boundary, but you can see it gets messy. So this thing is really more optimal for adding things at the end. And same with deleting. Deleting elements is only really efficient when you're doing it from the end because it's the reverse of the insertion. Doing it anywhere else just means shuffling and lots of mess. And this super large array also can't handle sparse data. You'll just end up with a lot of wastage. So see a lot of trade-offs built into this when we're designing algorithms for dealing with distributed data structures. This is the kind of stuff that goes into thinking about IPLD and how we build data structures on top of IPLD, and hopefully that kind of thinking is useful for your application. Further reading I've got for this, if you want to know more about IPLD and any of the things I've talked about, there was some links in the talk, but a lot of them you can reach through ipld.io. If you go there, that's our documentation site. We're working on that to make it more informative. We have a specifications repo on GitHub that's in the IPLD org/spec, and that includes a spec of this array, which we call vector. And it's also got a spec for a hash map, which is a hamped algorithm, which you'll see again and again in this world. Hamped is a hash array map tree, and it's a way of performing really efficient key value stores across very large data structures. And that's a really quite elegant algorithm if you want to look into the details of that, just to learn about how to think more about these things. That's it from me. I don't know if we want to do questions or we want to hop over straight to Chris. Chris, even on the call.
Let's do questions at the very end and just go to Chris right now.
Can you hear me okay?
will stop my screen share and hand over.
Can you guys hear me okay?
Yep.
Okay, just making sure I've had fun audio problems recently. And you can see my screen okay?
All good.
Great, thank you. So hi everyone, I'm Chris Hafey and I'm working with the IPLD team. And thanks Rod for that great introduction on IPLD. It just kind of occurred to me, I think as many of you coming from IPFS and Lotus World, you work with the APIs that are given to you, but there's a lot going on there underneath the hood, which is what Rod just went through. And one of the things the IPLD team is really focused on these underlying building blocks to basically build things like IPFS and Lotus and also your own custom applications. And today I'm going to be talking a bit about how the IPLD team applied these intrinsics to prepare very large data sets for Filecoin storage. And the project that we gave the name of it is called Dumbo Drop. And here's how my presentation is going to go. Basically, I'm going to give a quick overview of Dumbo Drop, talk about how we approach the problem, talk about the architecture, go through some lessons learned and tips and tricks in the end. I think our hope here is that you'll take some tangible kind of tidbits away, at least a better understanding of how we approach the very large scale data ingestion problem, and maybe some ideas on how you can do it yourself and solve your specific problems. So first of all, an overview. What is Dumbo Drop? Our goal was to process a very large amount of open data in a short amount of time for Filecoin. Mikhail Rogers, who's on the call, he's one actually the brains behind this. I kind of just came in and cleaned it up a little bit. So most of this design work is his handiwork. But we're pretty happy with the amount of data that we've processed. Over 3 petabytes of data has gone through Dumbo Drop. And it's amazing to see how it worked in terms of scalability. So if you are a performance person, a scalability person, you like cloud stuff, you're going to get excited by some of the things that we've done here. But that was our goal, is to process a large amount of data in a short amount of time. So how do we approach this? Well, most of our data was already in Amazon S3 buckets. There's public data sets like Landsat and whatnot, and we wanted to convert those into Filecoin. So one of the strategies we did is we decided to create our own custom application using the same underlying libraries that Lotus and IPFS uses. And so if you've ever looked at the Lotus or IPFS projects, you'll see all sorts of package dependencies, hundreds of them, made by Protocol Labs, some of them by the IPLD team, some by different teams. And so what we did is we said, to really get the type of scalability and performance that we needed, we kind of had to go a lower level than Lotus and IPFS. And so we went directly to the libraries and kind of stitched together this whole pipeline. Number 2 is we exploited AWS Lambda. So Lambda is a great capability of AWS serverless functions, and allowed us to get to a very high level of parallelization at a very affordable price. The other thing is, in terms of language selection, we actually didn't use any Go code. We wrote most of it in JavaScript, and the main reason for that is just for speed. We could really iterate quickly as we didn't have a lot of time, but we wanted to move quickly, and JavaScript allows us to move very, very quickly. We also use Rust as well, because there's some proof generation code that's written in Rust that's very high performance that we didn't feel like rewriting in JavaScript. And so we kind of leveraged that as well. So what does the architecture look like? Well, first thing is we kind of thought that we have a massive amount of data and we have to go through a whole pipeline. It begins in its raw state, and we have to have a couple output artifactors. So basically what you're seeing here in a vertical bars are the 3 stages: transform, aggregate, and COM key generation. Cutting across horizontally are kind of like architectural layers. So we actually have storage layer where we store data, processing where we do a lot of number crunching, and then indexing, kind of like a database. And so if I actually put kind of architectural blocks in here, you'll see there's 3 different S3 buckets. And we actually had, I don't know, maybe 30 or 40 data sets in the 3 petabytes. And so this is kind of replicated over and over again. But for each source data sets in a bucket, we generate output data in IPLD format and blocks. So when Rod was talking about CIDs and blocks, we actually took source files in S3 and converted them into IPLD blocks. And then also we generated car files. We had 3 different processing functions for each of the different pipeline stages. And down here, we use DynamoDB to store information about this whole processing logic as well as a COM key. So that's our high-level architecture. And I think one of the things I want to take away is think in terms of pipeline stages. When you're dealing with massive amounts of data, you don't want to basically do it all at one time. You want to basically break into stages, and you also want to think about these as different architectural components. So what happens? So the all data begins in the source data bucket. First phase kicks off, and what we do is we pull data out of here. So we kind of iterate over all the objects. We update the fact that we know all these objects in the database for tracking purposes, and then we convert them into IPLD blocks over here. And as Rod said, there is a block size maximum, and so sometimes we have to break a single file up into multiple blocks. And we do that. We keep track of all that in this source dynamo database. And so this takes days to run, even in parallel in S3. And I'll explain why it's kind of slow as we go on, but this is the first step. Second step is aggregating it up. So again, we take all this data we just produced, we run it through another Lambda function, we update the database, and we store car files. So this is like concatenating a bunch of IPLD blocks into a single big old file. Car is kind of like a tar file, but it's content addressable archive as opposed to tape archive. Same idea, it's a bunch of blocks back to back to back. And so that's step number 2. And then the third processing step is we take those car files, run through this Rust proofs code. This runs in the Lambda, and we generate com key, which is part of the piece proof that Filecoin depends upon. And I don't need to get into details of some of this stuff. In fact, this last thing I'm not going to talk about at all, and we don't even encourage you to get down to that level of detail because you don't have to. We now have things like PowerGate, which allows you to basically target IPFS as an output target in terms of your pipeline, and use PowerGate to shift it directly into Filecoin. So I won't get into more on car files and ComP for right now. So a little bit of lessons learned. That's basically what we did. Again, 3 petabytes worth of data ran through the system for a large number of data sets. Some things we learned, one is there are limits in AWS and S3 on performance based on prefixes. And so another name for them is directories, but Amazon calls them prefixes. And it'll actually throttle your, I guess, the ability to read from S3 based on how data is partitioned into different directories or prefixes. And as I mentioned early on, the longest phase that we had here was actually reading from the source data buckets. And this problem is one that we ran into, is that these source data buckets weren't really kind of organized or designed with this prefix limitation in mind. And so what you'd have is one top-level directory, call it foo, and then thousands and thousands of subdirectories and files underneath it. Well, S3 will limit on that one foo prefix, and so it was only so quickly we could actually go into that directory, into that prefix, and pull out files for processing. And so that was a huge bottleneck we ran into. If you're like us and you have basically an S3 bucket that you're reading from, you can't really change it, there's not much you can do. But if you do have the opportunity in terms of your pipeline upstream to partition your data with this prefix thing in mind, you'll have far better scalability and things will move much quicker. Another thing is when you're dealing with extremely large numbers of data, petabytes of data like we're talking about here, we actually start running into some reliability and performance issues in S3. I mean, this data is just so large and there's so much going on. It can be like a week's worth of processing sometimes for this stuff. Amazon will cycle servers, it'll scale out your infrastructure, all sorts of crazy things. And you have to, we actually ran into a lot of burps that we had to work around where it would get slow or start returning errors that we wouldn't expect that aren't documented. So one thing that we think of in retrospect here is that we should have had a prepare step before transform. So again, that first phase where we're iterating through the bucket was slow and unreliable, but yet it was also coupled with the fact that we were taking a file, breaking it into blocks and storing it. It would have been so much nicer if we could iterate through the whole bucket and then take that as input in one stage into another, and then just directly generate the IPLD blocks as output. Random failures do occur. Make sure your pipeline is resumable and build in retry logic. I have a couple of examples of some really nasty code that was in demo drop to make it work around these things. Again, we were trying to do a lot of data in a short amount of time, and we kind of not the most beautiful code in some places. And this is one of the area where it's like, what do you do? It's just we're getting errors we don't know and understand. AWS custom lambdas are tricky. If you have to do a custom lambda, like if you use like a non-standard language like Rust, the good news is there's a way to do it. We had our Rust proofs code that we didn't want to port to JavaScript, so we had to figure out how to get Rust into a custom lambda, and it was really challenging because the base Docker image that you build into is based on CentOS 6, which was released back in 2011, and tool change and whatnot change over time, and it's hard to get current tech sometimes to work with old tech like this. And so I spent quite a bit of time making that work. The other thing is there's a hard upper limit on lambdas in terms of RAM and disk. And so when we're dealing with large data sets, we ran into both of these issues in terms of our RAM consumption and how much disk we're using. And by the way, that includes temp files, the temp directory. So we actually had to modify the Rust proofs code to be streaming rather than just writing the whole thing to disk, and because we didn't have enough disk to do it. And we certainly didn't have enough RAM to do it. So it had to be modified to be a complete streaming-based implementation. Another lesson learned is compute is way cheaper than storage. And so we're dealing with petabytes and petabytes of data. The cost, AWS S3 cost goes up quite a bit. We actually found in 1 month, we were doing a lot of processing. Still only like a fifth of our cost was compute, 4/5 of it was storage. And in one case, we did this massive conversion, but we didn't quite need the data for, I don't know, another couple of months. And we did the math and we realized, you know, it's going to be cheaper to reprocess this huge like data set in the future than keep it in S3 for the next couple of months. So we delete it and then reprocess it a couple months later when we actually need it. So storage is expensive. And so when you think about this stuff, compute is cheap and plentiful. Storage is plentiful too, but it's just costly. So factor that into your design, just like we did. The other thing too is you need to be able to tune your concurrency parameters. Different data sets will run into different bottlenecks at different times. And so if you kind of hard code it or think, you know, if you get one data set to work, you've got one data set working. To get the next one, you may need to tune some parameters to get optimal performance. So build that in. That's just kind of good design, but it's especially important when you're talking about a highly parallel, highly concurrent system. And you know, not all the work we do at Protocol Labs is our most proud work. And this is an example, like I talked about, of us trying to move quickly and make stuff work in a short amount of time, and dealing with some kind of tricky things that we ran into with AWS. And so we had to build in retry logic all over the place with some kind of random timeout back off, just to make sure that when you have 1,000 parallel lambdas running out there, they didn't get into this kind of race, I guess, I don't know what you call it, but they're all hitting and the same time and overwhelming the system. So there is code like this. And also there's another example where we just get random errors that aren't really documented anywhere that AWS would give you as it's scaling out or dealing with kind of this load we're generating on it. And so just get ready to be prepared for not just solving the problem, but keeping your data pipeline running. It's not an easy thing. Tips and tricks. One thing like we did here is consider building your own pipeline from the same libraries IPFS Lotus use. You don't need to have use the IPFS or Lotus APIs for everything. You can actually create a pipeline like we did. We did pull in the libraries that they use to do things, and you can actually get much better gains in some cases by doing that. So don't be afraid to do it, although it does require some programming capabilities. Number two, exploit cloud services for scalability and cost savings, especially Lambda. Lambda is a great tool if you haven't done serverless before. It's extremely powerful and affordable. And it's really a way to get incredible scalability, which, by the way, when we're talking about, as Rod was talking about, we have an immutable content addressable data. Scalability is much easier than in, I guess, mutable systems that we're used to. And so it really kind of elevates your game in terms of what you can do in terms of data processing by thinking about scalability and parallelism. We talked about that prefix problem. One of the ways we got around it in our block store and in our car store is we use the content identifiers themselves as the object prefix. So content identifiers are highly selectable, and therefore they don't run into that concurrency blocking performance limitation S3 has. And so we put those in front and then followed it with that same CID as the object name. And we got around this bottleneck in terms of performance. And so phase two, as you remember, so phase one is to take all the data in the bucket and turn it into blocks. Phase two is to take that same data and turn it into car files. That second phase runs like 10 times, 20 times faster because we don't have this, even though it's doing basically the same kind of work, because we don't have this prefix problem. Fourth, transform your data into immutable IPLD blocks as soon as possible in your data pipeline. It just solves tons of problems for you if you can actually have data that is immutable. It's just a common theme. Mutability is good, and the quicker you get into immutable world, the easier and faster your life will get. The last thing in terms of tips and tricks, be aware that AWS performance will change as it rebalances while your pipeline runs. And so one of the things we had run into is we'd start up a big processing job and it would go really fast. And then, after a few hours, it would get a little bit slower. And then after a few hours, just come to a crawl. And we're watching the logs and we're like, what's going on? And then all of a sudden, boom, it goes into ludicrous mode and is scaling out like crazy. And what we're actually finding is that AWS has some kind of heuristics when, when a given account is doing a lot of, using a lot of resources, it'll try to start tuning it for your load. And when it's adjusting the load or rebalancing it, you kind of get these burps in the speed. And so don't be afraid of that. Get comfortable with it, because when you start moving into high scalability, massive graphs like this, you start pushing limits of what AWS can do in ways that no one else has done. Thank you. That's the end of my presentation.
All right, we'd love to hear some questions from anybody if you've got them.
Yeah. Did you do any cost calculations comparing Lambda to just using straight EC2s on like spot instances and stuff like that?
Yeah, I did early on. I mean, if you're really, really diligent about it, you can probably squeeze some more performance out of EC2. The issue is that just spinning up a box that has a bunch of cores that you're then going to balance into, the moment that you stop using it, you're just eating all of that. And so we were constantly tuning this and tweaking it and iterating on it as we were building it. And so it was just never going to be the case that we could always saturate all of our resources. And it was just like a massive amount of extra work to try to spin up some kind of clustering around all of this. And I mean, honestly, Lambda keeps getting cheaper and is like in general just cheaper to do anything with than EC2. I mean, the whole model for Lambda seems to be, if we give you basically free processing, you will generate data that you then have to store. And so like the model here is like Amazon just wants to eat all of your money in recurring storage costs. As an example, like we processed 2 petabytes of data, and the storage bill for storing it that month was 4 times the compute bill to process it. And the storage bill was going to recur every month if we didn't get rid of it. So there's just like a huge delta here. Like, yeah, so Lambda being like so flexible and so easy to use compared to EC2 was just kind of like an obvious win. And then we weren't really going to, split hairs on how much difference it was in cost to EC2, because the storage was always going to cost us way, way more. I mean, the main thing that you have to make sure that you do though is that like any other services that you talk to or any storage stuff that you talk to is in the same region, so that you don't hit the transfer cost as well. But other than that, it's pretty good.
All right, thank you.
I saw Pooja had a question. You want to go? I can't quite hear you for some reason. It doesn't say you're muted, but I can't hear you. There we go.
Okay.
Yeah.
Sorry about that.
No worries.
So I think you may have already covered it a bit, but I was just wondering if you could talk a little bit more about why you for Dumbo Drop, you why you're making the recommendation to transform the data into the IPLD blocks like as early as possible in the process.
Yeah, it's a good question. I probably didn't clarify the value of that, but once you move into a mutable world, you gain all sorts of properties that you don't have over the mutable world. So you have complete data validation. So you know that bit for bit, you can verify that the data you're working with hasn't changed. And that is going to save you, can save you a lot of headaches when you deal with diagnosing AWS failures and whatnot. Did it fully process this file? If so, how far? Do I need to pre-process the whole thing? And so by the sooner you move into a mutable world, you have your problem set, you have a lot more knowns than you had before in a very variable dynamic environment like AWS with large data. So that's probably one of the biggest reasons, but I can list many, many more. But the other thing is just tooling, right? So all of the Protocol Labs libraries works with CIDs and blocks. And so the sooner you get in that, you can start using all those tools to your benefit, as opposed to hand rolling your own tools and whatnot.
Also, Chris mentioned this really early on, but all of this is in a pipeline and there's different stages to it. And so when you find a bug in the pipeline, you realize you have to process a bunch of data that came like through that pipeline. And anything that you did before the immutable states, you basically just have to reprocess everything, because you have no guarantee, of nothing that you can check to really figure out like, oh, what data matched this and what didn't. Whereas like all the data that is actually like, once you hit an immutable state, you then have new immutable states or some immutable reference for everything after that. And so it becomes really easy to like go and find all the data that you may have messed up. And you know, you're going to have bugs, so you might as well plan for that early on.
I have another question too, which is just like for the for like Slingshot, or for people who are maybe just trying to like mostly, you know, for this competition or something, just say they want to, like, what would the recommendation? Because I know y'all were doing this for like an insane amount of data. It's like, you know, and I'm not sure the extent to which you wanted it to be like a super repeatable pipeline or whatever. But if someone's kind of like just like trying to do this as a one-off thing, what's like the easiest way to do it now, especially given kind of like what Chris was mentioning before, like Powergate is maybe a thing. I don't know how much that changes, but yeah, what would be the recommendation now if you were just trying to do a one-off ingest?
Well, I mean, it always depends on the amount of data and the shape of the data. So if you need to do a lot of data, and you know that if you were just to shove it into IPFS on your machine, it wouldn't complete until after Slingshot's over, then you have to figure out a way to parallelize it. And then the question is like, okay, do you have a bunch of data that is really large files, or do you have a lot of data that's a lot of really small files? And that really changes kind of the approach. But one big thing that I like, Chris mentioned this, do not do what we did, which was like actually create the car files into during comp and use the offline flow for the deals. That like you're going to run into a lot of things that just don't work as well as you want them to. But also, I mean, it's a really sort of unnecessary step unless you're shipping drives to people like we are. It's much easier to just like prepare the data in a format that IPFS can accept, and then get up an IPFS node connected to that data that you processed, and now you can use Powergate to do the deals, right? Like that's just way easier. And then, yeah, I mean, in terms of how you decide to parallelize the processing, like, you know, use Lambda if you need that much compute. I mean, we had to have them increase our concurrency limit from 1,000 to 10,000 just so that we could get through all this data quickly enough. Turns out that when you go up to over 3,000, though, there are other infrastructure things that will keep you from actually going above that. So you can't use it for our use case as much as you would like. But anyway, yeah, you know, maybe it's just using a bunch of cores on your machine and parallelizing that way. The thing to remember about these graphs, right, is that if you're doing operations serially, it's very slow. Like it's actually like one of the natures of these immutable data structures that they're really expensive to sort of create and mutate serially, but they parallelize incredibly well. So if you can figure out how to sort of isolate subcomponents of the graph, then you can parallelize all of those like as much as you want. And so for us, that really became like, oh, well, we can process every individual file. And then, you know, when we have a lot of small files, we'll hand like, you know, 100 or 1,000 files to one Lambda and say, go and do all of these, right? Or if it's a large file where we know that we're actually going to go over the time limit for Lambda, we'll cut that file up into parts and then give a part to each one, right? And so it really changes what you want to do based on the kind of the shape of your data. But the main thing to keep in mind is just that you can really parallelize the graph creation. That works really well.
Nice, thanks. And then, sorry, last question for me. What are some of the, like, I guess the fields that you maintain in the database that you use for like indexing all the information? What like pieces of information are important to keep around, I guess?
Do you want to take that, Chris?
Yeah, so, you know, I think we need to store the paths to like the source file and then the output blocks in the car file. So those paths I actually have it all documented. I need to refresh my memory. While I'm pulling up, why don't you answer, Michael, if you remember the one second.
Yeah, so one thing to remember that's a little bit unique about our data set and the way that we have to do it onto these car files is that each car file is like each car file is like about a gig. because that's how much we can kind of process in parallel. So we take a bunch of those and we do like one deal with them. And then we have information about that deal. And we need to be able to figure out like, okay, for this source data, for this one URL to a file, where is that in the Filecoin network, right? And so one of the sort of tables is just like all of those origin URLs for like, I think literally billions of files, maybe? I think we're in the billions now. And like a pointer from that to what car file is it in? And then we have a database of all the car files and their comp generation. And then from there you can go, oh, okay, well that's what the car file is. What deals did we do for that car file? And then we can find the deals and get the miner IDs and all of that. So we could reverse from there to actually access any of the data. One of the things that Chris did that was really good was we stopped using one table for all of the data and started doing a table per data set. So we have billions of rows, but they're now split across more. And then we have one table for all of the car files in comp, because there's less of those because we're compacting so many things together into one. I mean, there's still millions of them because it's like we did about 3 petabytes of data, but you know, it's not billions. Also, just Dynamo is terrible, and so it's really bad. And we have to, like, in each of these rows, we have to put a list of all of the hash IDs for all of the individual raw blocks. And so that actually gets like a little bit bigger than Dynamo tends to like having in a row. So we have like, you know, we have the one table that's doing that, and then it was really important to have like a different table for everything else in copy because we can actually keep that really small.
Awesome, thanks. And this this schema link is really helpful too. Thank you, Chris.
Yeah, the code is very cleaned up now and documented, and there's nice schemas because Chris took it over. I wrote most of this early code in like a 6-week, like, oh my God, we have to process this data right away, because it was literally like, we didn't know it. We had very early ship dates in our minds at the time. And it was like, literally like, we don't think that this will finish running unless I start running it now. And so I was writing it as fast as I could. And so it was a very impressive like thing that it was doing, but it was like the worst actual code I may have ever written. And so Chris did a great job cleaning all of that up. Cool. Yeah, I think we're at the hour now. Can we close that? All right. This was great. Thank you all for coming. Pooja, do you have any announcements or anything? Any final words for the Slingshot folks? No, you're done. All right. Everybody, have fun writing code.
Thank you all.
Say bye, Rod.
Thanks
Thanks, everybody.